this is Precision Stuff, and today we're going to be talking about the top 13 aluminum alloys you need to know about. You won't believe number 3. Okay, there's a whole wide world of aluminum. We're going to be talking about the wrought alloys, not the casting alloys, but we're going to start with the electrical alloys, and then we're going to go through some of the commodity grades, and then the high strength grades, and then some of the more exotic ones. And then for every single one of these, we're going to talk about a few properties in common, and then we're going to go talk about the special properties as well. So the first one is 1100 series aluminum, and that is 99% aluminum. It's commercially pure. So let's make our table here. So the first thing we care about is the yield strength, sigma Y. And to be frank, this stuff is butter aluminum. It has 35 megapascals yield. It's really soft. People don't use it for structural properties. The next thing we care about is the ultimate strength. This is when it breaks. That's about 90 megapascals. Still very buttery, very soft. You can bend it back and forth. It's very ductile though, which is actually why they use it for like wires and such. And then the elongation at break, that's in percent, that's about 40%. So you can really stretch this stuff before it breaks. Again, that's what makes it good for bending, forming wires. They draw this into like bowls and tubs and stuff frequently. And then let's talk about the thermal and electrical properties. Rule of thumb, so by the way, these are all in megapascals. The thermal conductivity K, which is watt per meter Kelvin, the more pure aluminum, the higher the conductivity. So this is actually going to be really high, 222. It's only going to get kind of worse from here with the structural alloys. And then the electrical resistivity, rho E, and I'm going to be giving you, like, if I say 3, it's 3e minus 8, and that is ohm meters, which is the proper way to do electrical resistivity, none of this ohm centimeter nonsense. And then here's like notes and comments. So very, very pure, very high electrical conductivity. It's about 3e minus 8 ohm meters. Copper is about 1.7, so it is like basically twice as bad as copper, but on a per mass basis and a per cost basis, aluminum bus bars end up being very compelling. So notes, it's basically 99% pure. It's used for like, bowls, wires. It's used for bus bars, soft and buttery and cheap. Cool. Let's get even more pure. Let's go to 1145. And what that means is it's actually 99.45% aluminum. There's higher grades. There's like 1199, but this is like one of the more common high purity grades. Again, super buttery and weak. Ultimate strength even lower, but the still high elongation. We're not using it for its mechanical properties. Thermal conductivity continues to climb to 230. This is basically as high as you're going to get. And the electrical resistivity falls to 2.8. Might not look like a big deal. It's like a 7%. If you're making a lot of wires and you're burning off a lot of heat, every percent counts, and this is often used for high-end bus bars. So bus bars, electrical, you wouldn't use it for much else. Cool. Number 3, which you're not going to believe, this is a really fun electrical alloy that also has really good mechanical properties, and it's called 6101T6. So, by the way, the 1100, 1145, those are strain hardening alloys. If you pull them, they get harder, so you might see like a 0 temper or like an H12, H18. It means that they stretched it, and it basically means that the mechanical properties went up a little bit, and usually thermal electrical go down a little bit. 6101 is actually quite strong. It's at 193 megapascals yield and about 221 ultimate. It's still got pretty good elongation, about 19%, so it's way less formable. You could still do like sheet metal stuff with it, but you can't like deep draw it very easily. Conductivity, thermally, still pretty high, 218, very similar to the high purity stuff. And the electrical resistivity, also quite good. So depending on the alloy, depending on the temper, somewhere between 3 and 3.3. So the T6 condition is like, is about 3. So, and then so notes, this is like a niche bus bar material, and it's not very common. It's mostly available in round bar stock, which is a very specific cross-section used for high voltage bus bars. They want it to be round so that when they coat it with like a powder coat or an insulator, it doesn't have sharp edges that like basically bleed high voltage. So not often available in the shape and size you want. Also, fun fact, it's used in aluminum foam for some reason. Fun material to know about. You can get really low density, like 0.1 gram per cc aluminum foam, pretty common for aerospace applications. It's similar to honeycomb, but it's isotropic. And these are, it's less pure. It's about maybe 97, 98% pure, but that's why it's still got such high performance into the thermal and mechanical, thermal electrical regime. Cool. Taking a step down to the kind of commodity grades. We're looking at 3000 series, specifically 3003. And you can get this in the 0 temper or all the way up to like the H18. Again, these are strain hardening alloys, so I'll write 0, I'll write 18. You're going to get somewhere between 41 to 186 megapascals. Again, that's temper variant. Somewhere between 110 to 200 megapascals yield. Sorry, ultimate. It's, not fabulous, but somewhere between 40 to 10% elongation. The higher temper, higher strength, lower elongation, lower temper, higher elongation. This stuff is not super, conductive, so like 193 to 159, and the electrical properties are like, okay, but not as good as the high purity stuff. This is a very common like pot and pan metal. This is good for deep drawing. It's very formable. Clearly, if you go to the higher tempers, you get higher strength, but you lose formability. It's also really cheap. And then the 3000 series in general is has plus magnesium in it. I'm gonna throw in a blue for magnesium, so plus magnesium. And the 6000 series overall is magnesium plus silicon, and we'll get to those later. So why do we use that? Pots and pans, pretty easy. Okay, more commodity stuff, 5052. This is your classic sheet metal box aluminum. And again, you get it in a variety of different tempers. The most common is like 5052H32. You're talking 193 yield and 228 ultimate. It's getting stronger, it's getting more useful. You can use it for structure. 12 to 18% elongation. You can still form it, bend it. Thermal conductivity is terrible, and electrical resistance is also much higher, 5E-3. This is not a good bus bar material, but this is classic like sheet metal box. This is like, I want to pay someone to bend something, and it has really tight bend radii because it's kind of soft, it bends a lot, it doesn't crack. So they also use a lot for like honeycomb in aerospace because, again, you can make a lot of tight little bends in it, and it's pretty cheap. Okay, now we're getting to the heavy hitters. This is 6061 T6. Okay, this is like your most common garden variety aluminum. This is the aluminum that put aluminum on the map. It is, if you ever see like aerospace grade aluminum, it's probably just 6061. It was aerospace grade in the 50s and 60s. It's really no longer. So 276 megapascal yield and up to somewhere around 310 ultimate. T6 is the aged, artificially aged and hardened condition. There's lower grades as well. We'll talk about this in a second. Lower strength. Again, decent, good elongation. You can bend it, but the bending radii are much higher than 5052. It tends to crack if you try to bend it super tight. Thermal conductivity not as bad as the 5000 series, but not anywhere as close as the electrical rated alloys. In general, electrical and thermal conductivity, very tightly coupled. Okay. Electrical, mediocre. This is your generic, you can weld it, you can machine it, you can extrude it, you can make bikes out of it, you can make airframes, you can make gears, you can make any sort of random bits and bobs. So this is like super common. Again, garden variety, super weldable. Every cheap bike is made out of 6061 T6. When you weld it, it basically goes down to the O temper condition locally. Very buttery, you'll lose at least half your strength or more. You have to be really careful about welding aluminum. You can heat treat it, basically do the artificially aging T6 condition to bring it back up to strength. It will distort things. You need to have careful fixturing, and you need to have a really big oven to do it in. So some people will weld it and not heat treat it. You just need to be really careful that that's going to be okay for your strength condition. And if you can't find a good table saying, 6061 with this type of welding gets you this strength, assume you're going down to the T0 properties, your yield strength and ultimate strength fall enormously. So be careful there. Okay. The next kind of common garden variety aluminum is 6063, available in a variety of tempers. I'm going to talk about the T6. This is not as strong as our 6061 friend. However, it's got a few cool properties. It, on a electrical, thermal, everything together, it's actually got a pretty good balance. So we're talking about, it's actually like strongly more conductive than 6061, but only a little bit weaker. And electrically, in the T6 condition, it's 3.3. In the lower tempers, it goes down to 3. That's what I meant to write up here. So this is used a lot in extrusions. It's considered an architectural grade. Like if you ever see like window glazings, they're extruded aluminum pieces. It takes anodization very well. It's corrosion resistant. But this is actually like a secret winner in terms of bus bars and like heat sinks because it's very common. It has high strength and it has pretty good electrical and thermal properties. So if you can't get 6101 because it's only available in flat bar stock, you can definitely make your part out of 6063 T6. You can get it extruded, you can get it in billet, you can do all sorts of wonderful things with it. So this is like a low-key bus bar material and heat sinks because of that combination. Like if you need to hold high pressure and move heat, really good place to start. Okay, now we're getting to the high strength materials. So this is what I would actually call an aerospace grade aluminum, something that's used for its high strength. That is, of course, 7075 T6. This is your most common high strength aluminum alloy. You can still get it really available almost anywhere. Yield strength, 400 to 500 megapascals. Really high. I'm putting in a high range there because it's thickness dependent. This is like a material people have studied in depth. If you go to MMPDS, the Metallic Materials Properties datasheet, or Mill Handbook 5, which it was based on, you'll see that for thin sections, you get higher strength. For thick sections, like 4 inches thick, strength goes down. Just like make sure you look that up, but basically high strength. And the yield is also, the ultimate is also fabulous, 460 to about 540. Also thickness dependent. Now we're gonna pay for that on elongation. It is higher strength. It doesn't deform as much before it breaks. We're also really not gonna wanna use this for a thermal or electrical application. Those properties are pretty terrible. So this is like not a good bus bar material. I mean, it's better than like titanium or something, but you really don't want to use this for electrical or thermal conditions. This is also not weldable. Not weldable. Yeah, technically you can weld it, but it will form brittle intermetallics and it will crack later. But this is really good for machining. So this is like gears and brackets and little chunks of secondary structure on airframes or little pressure vessels or other lightweight machine parts. Another key thing to note, the density is about 2.81 grams per cc. Typical generic aluminum, you assume about 2.7. It's denser because it's actually got like 5 to 6% zinc in it. So it's actually like the 7000 series is plus zinc, and it's got a lot of stuff in it. It's only like 90% aluminum. So this is heavily alloyed. You start to lose a lot of the friendly aluminum properties of electrical and thermal, but you get high strength. So the next one people use is 2024, and I believe the most common temper is T4. Also fairly high strength, not as much as 7075, but it has another property we'll talk about in a hot second. Higher elongation, lower strength tends to be in common. Again, this is a terrible, terrible alloy for electrical thermal properties. Literally, the resistivity is like twice that of pure aluminum. So do not use this for electrical applications. And this is also not weldable. This is a really good for machining. And the key thing that 2024 has, it's like a copper alloy. It's actually got about 5% copper in it. It is really good at high temperature, and specifically has high strength at high temperatures. People use it for brake pads in race cars. People use it for like high temperature aluminum pipes or heat exchangers or highly stressed areas that see high temperature. So at 200 Celsius, 2024 still has 138 megapascal yield, and 7075 would be down to about 87. So if you're looking for high strength at high temperature, you're gonna go with 2024, even though it's less strong than 7075 at normal temperatures. So that's why it's specifically used in high temp applications. High temp for aluminum. 200C is not that high in the grand scheme of things. Like steels go to like 4, 5, 6, 700, 800 Celsius. Stainless go above that. Inconels go even higher. But if you're working with aluminum and light metals, this is actually pretty good. In general, most aluminums will lose the vast majority of their strength by 200 Celsius. Now, we're talking about exotics. These are way less common, they're harder to get, they might not be available in the shape and size and flavor you want, but they're worth knowing about because they have pretty special properties. So 7068, I have no idea what temper it comes in. The 7000 series has really been milked for the last decade or two. People are coming out with more and more advanced alloys here, specifically for aerospace. So these are, again, zinc alloyed, they're good for machining, they're not weldable. You can get some insane strength out of high-end 7000 series. This is crazy strong. This is a pretty good steel strength in an aluminum. It's wild. Again, you're paying for it with elongation. It gets more brittle at higher strength. Shockingly, this alloy has good thermal properties, still not good electrically. This is now you're in aerospace and you have a bracket and you have money and you're going to use the money to make the bracket lighter. I don't know much about its other properties at high temperature, but basically there's always a better 7000 series out there if you're willing to pay more. Note that the density is actually up to 2.85. It's only 85 to 88% aluminum. It's actually got copper, magnesium, zinc, and a little bit of zirconium in it. Maybe the zirconium helps at high strength. Okay, now we're getting to the really exotic stuff. So you can make aluminum-silicon alloys, and you can make them basically anywhere from 100% aluminum to 100% silicon. And we're going to kind of look at some of these extremes. So the first one we're going to look at is a 73% aluminum, and then we're going to go down to 50%. These are hard to make. Either you use powder metallurgy, so Sandvik has a Sandvik Osprey category of powder metallurgy, or you do some really rapid cooling of flakes, some exotic process. If an alloy has a name, Sandvik Osprey, it means it's expensive. If it has just a number, it means you can probably get it. This is very difficult to find, and you use it for some very specific applications. So we're going to walk through 282. This is actually about 189. These are not terribly strong, but they have some very specific properties we'll get to in a second. The reason why you'd use these, and also I don't know their elongation at break, but I know that their yield strain is quite low, so probably low. They don't have fabulous thermal properties or electrical properties either. Why would you do this? Well, when you mix aluminum and silicon, you tend to get something that has a higher modulus, a lower density, and a low CTE. So typical CTE of aluminum is about 24 microns per meter Celsius. That's just how much it expands. This alloy, the CTE, is actually only 17 microns per meter Celsius. The Young's modulus is 92 gigapascals. That's basically 50% higher than normal aluminum. Typical aluminum is 69 gigapascals. So it's much stiffer, and the density, rho equals 2.6, a little bit lighter. So why would you want this? I want a material that is stiff and light. That means it basically has high dynamic performance. You can basically make optics or mirrors or space telescopes or high speed moving precision machines in semiconductor, and they weigh less and they're going to vibrate less and they're going to expand less. So this is good for precision machines. When you go all the way up to 50-50, it gets even more extreme. We're talking 11 parts per million CTE. That's basically what typical steel is. So you have an aluminum alloy with the expansion of steel. The Young's modulus shoots up to 121 gigapascals. That's about titanium. That's very impressive on a modulus to weight ratio, and the density falls even more to 2.5. Again, you're losing strength, you're losing other properties, but this is very specific for precision machines, optics, anything that has to maintain a shape across temperature and vibration conditions. Okay, now we're getting even more exotic. This is stuff that you, again, might not ever use, but it's good to know about it. And this is actually not really an aluminum alloy, it's a beryllium alloy, and it's albumet. Specifically, it's albumet 162, which means it's 62% beryllium, so it's not even really mostly aluminum, so this is kind of fake, it's slid in here. Strength, okay, 276, about 400. Why would I use that if I could just buy 6061 or 7075? It's not amazingly ductile either. What it does though, it's again used in these similar applications. I'm just gonna jump around on my table here. The density is a shocking 2.1, very, very low density. The modulus is an insane 193 gigapascals. This is about as stiff as a typical steel and weighs 4 times less than a typical steel. That's incredible. And the CTE is about 14. So this is basically something that has the thermal and stiffness properties of steel that weighs 4 times less. Also thermal conductivity, K equals 210. It's actually shockingly good. So this is the very high-end version of these aluminum-silicon alloys. Again, used for space telescopes, mirrors, optics, even some aerospace electronics housing where you need it to be stiff, light, and thermally conductive. You're not going to find this very often. A few last ones. You'll see something called all-clad. And this is basically where they take another alloy, usually 7075 or 2024, and they put a thin layer of aluminum 1100 series on the top. So you basically get a sandwich, and they put a thin layer of that. It's used for corrosion. So basically these alloys, the higher strength alloys tend to have a little bit worse corrosion properties. If you're in extreme conditions, getting the plating helps. I think it might also help with weldability. Don't quote me on that. You usually lose a tiny bit of strength because you're just, a little bit of your section was replaced with butter aluminum. But that's also something good to know about. You'll see it often. And then last few, if you're in exotic aerospace land, there's 2195T8. This is an aluminum lithium alloy. It's actually quite strong, talking about 520 yield, 552 ultimate, 5% elongation. And this is weird because it has silver and copper and lithium. This is commonly used for large tanks and rockets. So this is what the Falcon 9 is made out of. This is what I think some other aircraft, maybe the A380 or some of the aircraft, spacecraft, big tanks. So it's weldable. It's pretty strong. Some of the problems are it's not very corrosion resistant. Like when you add lithium to something, the lithium is very reactive. So the lithium on the surface will react and basically rust and fail over time. This is why rockets don't love being left out in the ocean. However, they're always launching next to the ocean, so it's kind of a compromise. But it's another kind of high-end alloy that people use. So lithium alloy. That's basically the summary. There's a whole bunch more you can talk about, and even talk about the casting alloys. Casting is kind of lame. The properties are usually worse in terms of mechanical and thermal and electrical. The contrast is you can make it into almost any shape you want. It's usually a lot cheaper. It's worth mentioning A356. This is your most generic cast aluminum alloy. It's basically melted down beer cans and wheels, like people with aluminum alloy wheels. You're not going to get fabulous properties and control over it. It has tons of porosity when you cast it, but it's really cheap. So I'm not going to go into that, but thank you for listening to Aluminum.